have a brief recap of last time. So we finished with the introduction of spinors and SU2. And so the point was that the Lie algebra of SO3 is actually the same as the algebra of SU2 and has a two-dimensional representation, which is given by the Pauli matrices, essentially given by the Pauli matrices. And to normalize the algebra to the geometric normalization of the algebra of rotations, the geometric 3×3 T's correspond to the Pauli matrices multiplied by the square root of -1 and divided by 2. And that 2, so you have these this two-dimensional representation, and then you can ask what are the objects on which it acts, and these are spinors. And as we go on, and especially as you do the quantum field theory courses, you will understand that these spinors, or fields, spinor fields are what you use to describe fermions in particle physics. And then we finished by emphasizing the importance of this factor 2, namely that in a geometric rotation, if you shift any of the angles by 2 pi, you're just rotating a vector back to itself. So you get the identity. It doesn't change the matrix. Whereas in the two-dimensional spinor representation, the 2 pi rotation actually is non-trivial. So, which means that spinors will change sign after undergoing a 2 pi rotation in space. And that's expressed through this change, through this expression for the SU2 matrices, of which these are the ones which correspond to matrices R by taking the exponential map of the same pair of corresponding generators. Here we were just proving that we actually get SU2. And so the point here is simply that a general real linear combination of the I sigma over 2 matrices is a general anti-Hermitian 2×2 matrix with 0 trace. And its exponential, which is this SU2 matrix, will be unitary and have determinant 1. So unitary because the exponent is anti-Hermitian, and determinant 1 because the trace is 0. We use this as an excuse also to introduce the groups UN and SUN. And so the first line here is something we've proven now. And this 2 pi, this sort of minus sign that you get by making a 2 pi rotation means that SU2 contains twice the number of elements of SO3. Because
Professor, I think the audio,
yeah,
we cannot hear you right now.
yeah.
the amount of batteries.
This has to be either off or paired. Now they should hear you.
Okay.
Do they?
Can you hear us on this one?
Yes,
Yes, we can. Yep.
Oh, and it's okay. We're going to put the other one on in a second. But is there a way for me to disable this one? Like from the screen? From the
no,
screen?
No,
No.
you have to do it from here.
Okay. There's something wrong with that thing then.
Why don't we do this?
I'll just,
If you don't mind, just go on with that. Let me see what I can do, and I'll be back in like 15 minutes.
sure. Okay. All right, we're going to go on with this one for a minute because we can't, there's something wrong with that one. So SU2 modulo plus or minus 1 means that for all elements of SU2, G is considered to be equivalent to minus the identity times G for all G. Okay, so this this defines you a new group, this equivalence relation. So, you know, if I have any element of SU2 and I consider minus the identity times that element, instead of considering these as two separate elements, I now define a new group in which they are the same element. So you've divided SU2 into two halves, in fact. And those two halves independently are also a group. And this group is isomorphic to SU3. Okay. I think I wanted to set an exercise. No. All right. Are there any questions before we proceed? What we're going to do next is work towards the representations of the Lorentz group. No? Okay. So I'm going to switch over to... I decided to write separate notes each week because the PDF file turns out to be something like 15 megabytes or something, and if we keep going on like that, it'll get too big. All right, so we've already demonstrated that the Lorentz algebra in 3+1 dimensions is two copies of the Lie algebra of SO3, or equivalently, two copies of the Lie algebra of SU2. And this is just a copy of the slide we had. So if you remember, we took the boosts and the rotations, and we took the sum and the difference of boosts and rotations, and that gave us three generators Ni, which obey the SU2 algebra, another three generators N tilde I, also obeying the SU2 algebra, and the Ni's commute with the N tilde I's for all I and J. Okay, I'm going to now. So this came out, and we've shown it, but I want to kind of understand a little bit. I want to elaborate it a little bit further. Okay. So a boost. I remind you that a boost in 1+1 dimensions is given by this matrix of hyperbolic sines and cosines. Now, if I take this matrix, M, I take its transpose, I multiply by so I take the transpose, multiply by this matrix, which is just the Minkowski metric in 1+1 dimensions, and I multiply by M, and I get back the Minkowski metric. Okay? So what this equation says is that eta, the Minkowski metric, is preserved by Lorentz transformations. So in other words, this equation is equivalent to Lorentz invariance, or which in 1+1 dimensions is just invariance of the interval. So let's see this in more detail. So sorry, I think there's a typo here. So yeah, this is because the interval is the transpose of this vector. Now, normally I could write here, instead of the product of the Minkowski metric with the vector, I could have written just the vector CTX. But instead, I'm going to write it as the Minkowski metric times the vector CT minus X with component CT minus X. Now, I do the next line is the Lorentz transformation. So I'm going to take the Lorentz transformation on the right-hand side of CT of the vector CT minus X. And on the left, because we've got a row vector, it's transformed by the transpose. And so you see that this is also equal to the inner product between the transformed vectors. But you see the thing in the middle the thing in the middle is actually has the elements of the formula from before. So because of equation star, all of these things are equal. So that's why Lorentz invariance is equivalent to this equation, M transpose times the Minkowski metric times M is equal to the Minkowski metric. Okay. So you'll see this type of definition of the Lorentz group in books as well. All right. Now, this is actually very much like something we've seen before. It's like the definition of SON. Definition of matrices in SON are determinant 1 matrices which are orthogonal. Which is, you take the transpose, well, it says that the transpose times the matrix is the identity, but I could have put in the middle, sandwiched in the middle between the two matrices, the identity matrix, 1, or sometimes we write that as delta. And so, yeah, this is wholly analogous to this. The only thing that's different is that you replace delta by eta. And because of this, in 1 + 1 dimensions, the group of determinant 1 Lorentz transformations is called SO1,1. That's because you've got 1 space direction and 1 time direction. And in 3 + 1 dimensions, it's called SO3,1. Because here we're going from a sort of signature n, 0 delta to a signature n minus 1, 1 eta. So it's really the signature of eta, which is sometimes also called the bilinear form. Now note, if I start with 1 + 1 dimensions, and I take the interval, and I make the transformation where I take t, I redefine t as I times something real, which for convenience I'll call y divided by c. Then under this analytic continuation to imaginary time, we get minus y squared minus x squared. So minus y squared minus x squared is SO2 invariant. So under this analytic continuation, SO1, 1, becomes SO2. And similarly, in 3 plus 1 dimensions, SO3, 1 would become SO4 by the same transformation, and just add on the other two coordinates. So what we're going to do now is look at, is it now? Yeah. Well, we're going to look at SO4 in the same way that we looked at SO3 before, and rederive the algebra. All right. Now, before we do that, we're going to start introducing the 4-vector notation, or the Lorentz vector notation. Okay. So the thing that I started with, we can rewrite in the following way. We're going to call the vector, the column vector x lower mu. So in this case, mu can take values 0 and 1. X0 would be CT and x1 would be x. And similarly, x upper mu would be the row vector on the left. And once we do the Lorentz transformation, we get the primed versions of those. Can you still hear me?
Yes.
Yes, we can.
Yes.
Yep.
So in the 4-dimensional case, x lower mu is a 4-vector. So mu goes from 0 to 3 in our, in many conventions. And these vectors with the lower index are called covariant vectors, or covariant 4 vectors. X upper mu is what you get by taking the Minkowski metric and acting on x lower mu and taking the transpose. So, I mean, where I'm taking the transpose in the sense that if I multiply a matrix by a row vector, I'll get, sorry, by a column vector, I'll get a row vector. So the vector with the raised index will have entries which are the same as the entries as x lower mu, except there will be minus signs where the minus signs of eta are. And in our conventions, we're using the mostly minus convention for eta. So the interval in Einstein summation, using Einstein summation convention, is just written x upper mu, x lower mu, okay? And that's equal to x upper 0, x lower 0, plus x upper 1, x lower 1, plus the other two terms. And because x upper 1 is equal to minus x1, you get minus x1 squared here, and so on. Are there any questions about this?
Can you briefly explain the origin of the name covariant and contravariant vector?
Well, it just means that well, there's a mathematical description which you may not find satisfying. It means that if you think of these as vectors on the space-time manifold, one of them is a section of the tangent bundle and one of them is a section of the cotangent bundle. But from a pedantic point of view, it just means one transforms naturally. If one transforms by the matrix M, the other one transforms by the transpose of the matrix. It's just to keep that distinction. But mathematically, they are slightly different objects. But for most applications in special relativity, it's just the transpose of the matrix that makes a difference. Okay?
Okay, thank you.
Now, on just an operational point, we can think of eta mu nu as an object that we use to raise the indices. So, over here we had the definition of x upper mu in terms of x lower mu and the Minkowski metric. So let's take that it's important to remember that we can then just use eta mu nu to convert something with a lower index to something with an upper index. Okay? And similarly, the same matrix, but written with both lower indices, so eta lower mu nu, can lower indices. So you can do the inverse operation. So usually the transpose is dropped from this expression, but it's implicitly understood that x upper mu is a row vector. Yeah, I mean, another way to answer your question, by the way, which is equivalent, is that x upper mu and x lower mu, if x lower mu is a 4 vector that takes values in some vector space V, then x upper mu takes values in the dual vector space, which is the vector space whose dot product with V will give you real numbers, not some real numbers. All right, so we've been using x mu, but there are many 4 vectors that play roles in physics, and also objects with more than one Lorentz index. So a 4 vector V lower mu is simply one that has the same transformation properties as x lower mu. So this is just the definition. Later on, we will look at we will be working with different examples of 4 vectors and 4 tensors, which are objects that have more than one Lorentz label. And you will throughout your courses. Just a note, because I'd recommended for some of this stuff, Landau and Lifshitz, they don't use mu and nu, rho, sigma, Greek. They don't use Greek indices for their Lorentz labels, but they use Latin ones. Whereas the majority of texts use the Latin IJKLM or the spatial components of the vectors, and that's what we will do. But you can use any labeling system you like, as long as you're consistent. All right. Now, so we have our matrix, our Lorentz. We have our Lorentz matrices in the Lorentz group. So clearly, if I set mu equals to I and nu equals to j, that gives me the rotation matrices, the rotational subgroup of matrices in the Lorentz group. So now the R's are SO3 matrices. All other types of, any other element of the Lorentz group which is not a rotational one will contain some sort of boost. So there'll be some, in some way of writing it, there will be hyperbolic sines and cosines around. Okay, well, let's do this analytic continuation that I talked about before, which would then take SO3, 1 to SO4. And what I want to do for the remainder of today is understand the Lie algebra of SO4, and then how it relates to the Lie algebra of the Lorentz group that we derived before. And then we'll go on to talk about how to construct the representations. All right, now, if you remember when we did SO3, the algebra, we pointed out that the algebra is naturally thought of as the set of 3 by 3 antisymmetric matrices, where the algebra product is the commutator of these matrices. So it's not just matrix multiplication when we're talking about the Lie algebra, it has to be the commutator. I just wanted to be specific there because sometimes people you might see in texts that the Lie algebra of SO3 is the set of antisymmetric matrices, but then they don't qualify that what the product rule is on that algebra. And that can be confusing because you can multiply antisymmetric matrices together to get other matrices. Okay, anyway, it's a fact that the Lie algebra of SON in general is the set of n by n antisymmetric matrices with commutator as the multiplication rule. So why is that? Well, the reason is that in n dimensions, a rotation takes place in a in a plane, a two-dimensional plane. So in 3 dimensions, we're used to thinking of that as rotations about the axis, which is orthogonal to that plane. But you can all equally just describe it by the coordinates in that plane. So we were looking at a Cartesian system in which you can then think of it as the XY plane, the XZ plane, and the YZ plane, or maybe more conveniently, the 1-2 plane, 1-3 plane, and 2-3 plane. So you can see that for n equals 4, we have 6 2 planes, which would be 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. This is actually n choose 2. N factorial, no, n minus 1 over 2 in general, because it's pairs of indices which are not equal. And the matrix is antisymmetric because the rotation has an orientation. You rotate one way. We fix the convention so that we have this generator 0, 1, minus 1, 0. If I multiply it by minus itself, it corresponds to rotating the other way. So we can build up the generators as we did before, but now we label each generator by a plane. So T12 has entries only in the 1, 2 direction. 1, 2 entries of the matrix, etc. T13 is in the 1, 3 directions, and just keep going. Okay, so one can show, and this I'll leave as an exercise for you, that in 4 dimensions, the 6 Tij's that you get, if you take an arbitrary linear combination of them, you can construct any antisymmetric matrix in any 4x4 antisymmetric matrix. And actually, in general, in dimension n, you can do the same. So that means that an antisymmetric matrix A, big A, with matrix entries A and B can be written as the sum over K and L of some constants, A, K, L. And in 4 dimensions, there's 6 of them, times the TKLs. And I've explicitly indicated that TKL for each K and L is a separate matrix with indices A and B. Of course, for each of the TKLs, it's only the KL entries of the matrix which are non-zero. But I've called them A and B because I want to avoid confusion in the future. So this is what a general antisymmetric matrix looks like. All right. So what we're going to do next, but we're going to take a little break first, is we're going to look at different combinations of the generators, and we're going to show that we get 2 copies of SU2. So similar to what we did before, but for this compact group, the SON. So SON for any n is compact because each of the where is it? Sorry. When I exponentiate these matrices, I can think of A12 as an angle of rotation in the 1-2 plane. And so all of these A's they all run from 0 to 2 pi. And that means that the set of all SON matrices is compact. So yeah, we want to show the relationship between SO4 and the Lie algebra, the two copies of the Lie algebra of SU2. But yeah, let's take a 10-minute break. So we'll come back at, I don't know what your clocks are, but mine one says 47, so we'll come back at 57. Okay, so can you hear me?
Yes.
Yes.
Yes. So here now, I'm going to redefine the 6 generators into 3 that I'll call S plus with label 1, 2, and 3, and 3 that I'll call S minus with labels 1, 2, and 3. So these are the combinations of generators which give you the 2 copies of the SU2 algebra. So S plus I, they satisfy the SU2 algebra, as do the S minus I's, and they commute with each other. So it's a bit of a slightly painful exercise to verify that, but I want you to verify that as an exercise. So this establishes that SO4, the Lie algebra, is 2 copies of the SU2 Lie algebra. And therefore it's also isomorphic to the Lie algebra of the Lorentz group. Just to give you an idea, to show how this works, let's look at the commutator of S1 with S2 for the plus case. Okay, so S1 is 1/2 times the sum of, where is it? The 1-2 generator and the 3-4 generator. So you see here we have the 1-2 entry and the 3-4 entry. And S2 is minus the 1-3 generator plus the 2-4 generator. So we have entries in the 1-3 and 3-1 and 2-4 and 4-2 with the appropriate signs. And the quarter is because we've got the overall factor of 1/2 for both of them. So if I multiply S1 with S2, get this matrix here. So you can see, for example, this one comes from multiplying this one with this one, and so on. And then when I subtract off the S2 times S1, I get minus a quarter of minus the matrix that I've got that I first computed.
Professor, when you defined the S plus minus matrices on slide 21, I think there wasn't any plus minus sign on the definition. Like,
oh, sorry. Yeah, thank you. Thank you for pointing that out. Good. please, if you spot any typos, speak up so then I can correct the slides in real time. Okay, so that then these two terms add up to give you 1/2 times this matrix. And this matrix is antisymmetric in the 1, 4, and 4, 1 direction, as well as the 2, 3, and 3, 2 direction, which is S3 plus. Okay, so then I'll leave it as an exercise to check all of the other ones. So now, SO4 is actually the exponential of these two copies of the Lie algebra of SU2 times SU2, but because it's compact, you actually do get SU2 times SU2. You don't quite get that, you get an overall Z2, which is basically the same Z2 that distinguishes spinor representations of these two SU2 factors from vector type representations of SO4. So this Z2 is very much like the Z2 that we had when we were showing that SO3 is SU2 mod Z2. Okay, so now if we do the analytic continuation back to take SO4 to SO3, 1 effectively, then the 6 generators that we started with go over to the 6 generators of the Lorentz algebra, namely the 3 boosts and the 3 rotations, where essentially if you take, since we're picking the 4th direction as the one that becomes time, essentially means that these 3 get mapped into a linear combination of these 3. And the remaining 3, the ones without a 4 index, become the rotation generators. And this is not, I mean, the correspondence is 1-to-1, but there are signs and permutations to take into account. And you can verify which of these goes over to the T hats, as I was calling them in the conventional case, to match the notation there. So up to these signs, which you can work out for yourselves, S plus goes over to the ends and S minus goes over to the n tildes. All right. So now, having established this, we can start talking about the representations. So what we're going to spend the rest of the time today and probably a little bit more on Thursday doing is studying the representations of these two isomorphic Lie algebras. So because the Lie algebras are isomorphic, their representations are isomorphic. They have different physical meaning because the Lorentz group is non-compact, whereas SO4 is compact. So we've got 2 copies of SU2, which means that I need to pick a representation of both of them. As we reviewed, and I guess you might already be studying in more detail the SU2 representation theory, The representations are just given by choosing a spin, which can be an integer or any half integer or integer. So we choose a spin for each one, each of the two SU2. So we have J1 and J2. And J1 stands for the 2J1 plus 1 dimensional representation of the first SU2, and J2 denotes the 2J2 plus 1 dimensional representation of the second SU2. This doesn't give us yet a representation because we have to figure out how to get the right matrices from it. So next. Now, we know that the n's and n tildes commute with each other. The two SU2s commute with each other, which means that we have to find matrices such that these two representations commute with each other. So I'll put this in parentheses here because what do I even mean by that? Because these two representations are of different dimension. So this expression on the right-hand side doesn't even mean anything yet. So the purpose, so our task now is to give some meaning to this expression. So a representation of the algebra of interest is a set of 6 n by n matrices, 3 which represent n, the n's, and 3 which represent the n tildes, and obey all of these relations. So we actually have to construct, so these guys have to be n by n matrices, and these have to be n by n matrices of the same n, but somehow related to the SU2 representations, which have different dimensions. So the way that works is what's called tensor products. Okay, so let's now consider a general group G, and let's say that we're given 2 representations, one of dimension m, one of dimension n. So what that means, so we've talked about the algebra representations. Here I'm talking about group representations now. It means that if you give me the group element, 3 group elements, G1, G2, G3, where G1 composed with G2 is G3 as the abstract group relation, and a representation means that for all elements of G, it means you take, if I have the representation of dimension m, means that there's an m by m matrix which represents G1. I take that matrix and I multiply it by the corresponding matrix that represents G2, and then the answer I get from doing that multiplication is the matrix I get which represents G3. So a representation is this homomorphism between the elements and the matrices. And the same relations are obviously true for any other representation of dimension n. Now, from this, from the m and the n dimensional representation, I'm going to now construct a much bigger representation of dimension m times n. So in order to do this, I'm going to have to define for you what this symbol means. And this symbol is called the tensor product. It's easy to understand it just by looking at some examples. So the definition of the tensor product of these two, this pair of 2 by 2 matrices, I'm going to take them and construct a 4 by 4 matrix. And the way I do that is I take the first matrix, take its elements, and for every element, I multiply by the full matrix on the right. So actually, I should say this in a bit clearer. So what I mean here is the 4 by 4 matrix whose elements are AE, AF, AG, AH, BE, etc. The bottom entry would be CG, DH. Is it clear what I mean by this tensor product?
Yes.
Yes.
Does anyone have any questions about it? Okay. So notice I could have done it the other way around. I could have taken the matrix on the left and multiplied by the elements on the right. So this is just a convention. So when one's working with tensor products, one has to keep a consistent convention. So I'm choosing this particular convention. And it should be pretty clear that you can do this for any pair of matrices, even of different dimensions. Similarly, you can do it with vectors. So if I take two component vectors, I've got V and W, both 2 component vectors. Then I do the same thing. I take the elements of the left vector and I multiply them by the vectors on the right. So here explicitly I've written out what the tensor product between these 2 vectors is. The tensor W in a more compact notation. And this has the nice property that if I now consider a matrix, a 2 by 2 matrix acting on V and a 2 by 2 matrix acting on B, that generates me 2 new vectors, and I can take their tensor product. And that operation is the same thing as taking the tensor product. This is the same thing as taking the tensor product of the 2 matrices and acting on the tensor product of the vectors. So here you can, I've given you an exercise here to verify that this is true. You could take, for example, for A and B, sigma 1 and sigma 2, or you could do it for a general matrices. So now, if we go back to our m and n dimensional representations, it means that the point is simply that the tensor product between these 2 sets of matrices is actually a much bigger representation. It's the tensor product representation. So we can verify that using the property that we just discovered. By looking again at G1 times G2 is G3, well, there's an RM for G1 and an RM for G1 as well. I can take their tensor product Then I can multiply it by the corresponding thing for G2, which is this big matrix here. And now, the first line is equal to taking the product in the m-dimensional representation of G1 and G2, tensored with the same thing in the n-dimensional representation. Well, the first bracket is just the m-dimensional representation of G3, and the second bracket is the n-dimensional representation of G3. So this proves that we get a representation this way. Are there any questions about that? Okay. So this is a way of getting representations of the group. In physics, in many physics applications, we normally practically working with representations of the, if G is a Lie group, we usually work with representations of the Lie algebra. So that's our next task, is to work out what the representations are of the Lie algebra by undoing the exponential map. So now to find representations of the Lie algebras of the two orthogonal groups. By sort of undoing the exponential map. So let's start with so for SO4, we have the generators S plus I and S minus I. Or just think of the, which are just those linear combinations of the TIJs that we defined. So so a general, let me say a general representation, general group representation. Call this RD, just so don't get confused. Is a sum is the exponential. Sorry, I'm going to write this on the next page. Space. So we'll have 6 parameters because we've got 6 generators. And it's the exponential of the sum of theta I plus Si plus theta minus Si minus. Sorry, this is also not correct. So here we'll have d I plus j1 so this is some representation of the first SU2. Now we tensor that with a sum of theta I minus d minus j2. So the first exponential is simply the matrices of the 2J1 plus 1 dimensional representation of SU2. This second guy is the spin J2 representation of SU2. So D here, who can tell me what D is?
They are the generators of the group.
No, this D here.
Yeah, the generator of the group. D. Okay, D small here.
The small d.
It would equal to, then parentheses, J1 plus J2 plus 1.
No, that's not correct.
I mean, no, 2 times all of the bracket.
Say it again, what the full answer
Okay.
is.
Okay, the first representation would have the dimension 2J1 plus 1. And the second would have 2J2 plus 2. Yeah, times. I added them. I'm sorry. Okay.
All right, so that's because this matrix has dimension 2J1. Thank you, by the way, 2J1 plus 1. And this matrix has dimension 2J2 plus 1. And the tensor product gives you a representation which is the product of the dimensions, which was m and n before. So this is the representation, the tensor product representation of SU2 times SU2, the group. And it's also a representation of SU2 times SU2 mod Z2. Okay. So now that we have the tensor product representation, what we have to do is just expand the exponentials. And that will give us the algebra representation matrices. So let's do that, and then we'll finish, and then we'll next time we will explore the formulae in more detail. Now, exponentials as Taylor series. Okay, so then this R D plus minus I. So now D plus I minus J looks to be different. So this was exponential of some matrix D in the spin 1 representation of a function of theta plus tensor. So I've just compactified the notation because you don't have to specify the sum. This is tensor product. So the exponential always starts out. So I'm going to, I'll write this as one series tensor the second series. Okay. So the first, what's the first term in the exponential expansion of the first factor? I'm asking you guys.
Yeah, like the identity plus.
Maybe someone else instead of Mohammed should answer.
Okay.
Sorry, Mohammed. Is anyone else actually listening?
Yeah, Professor.
So Gustavo, what's the first term here?
Okay, so here we are going to take 1.
1. What does 1 mean? Which
And
one?
the identity in a group.
Yes. And what dimension is this 1 in this particular case? This is the identity matrix, but of some dimension. Do you know which dimension? So it's the identity in the spin J1 representation. So the spin J1 representation has dimension.
Oh, J1 times J1.
No, it's 2J1 plus 1.
Oh, yeah.
But that's okay, because you're still getting used to SU2 representation theory. Okay, then the next term is just this ordinary addition. And what will it be? Remember, e to the x is 1 plus x plus x squared over plus. So what am I going to get? I need another matrix here now.
Yeah, so in this case, we will have DJ1.
DJ1, good.
Yeah.
plus all of the other terms. And
Mhm.
I'm going to ignore all the other terms because by definition, you don't need them. Okay, so similarly, this expression, the second factor, will be the same, except you exchange J1 with J2. That's it, okay? So finally, we just have to take this tensor product. So that equals, there's one term at the beginning, which is a big identity matrix from taking tensor product of 1 with 1. And I get the identity matrix in dimension, which is the product of the two dimensions. That's the first term. But then I get, this is the all-important term, the first identity matrix, tensor, the second representation. And when I do it the other way around, I get dj1 tensor, the other identity matrix, plus higher order terms. So just to repeat, the first term we wrote was this times this, then we wrote this times this, and then we wrote this times this. Remember, the order is important in the tensor product. So this is a J2 here. So this is what we get. And this whole thing is supposed to be the exponential of the thing we're after, which is some representation of labeled by J1 and J2. Well, we get the identity matrix here, and then this is the first term, the generators. So we can expand. So I wrote this in this compact form, but remember that dj2 is the sum of the representation matrices times the angles, theta minus. And similarly, for theta plus. So therefore, Ni is represented by dj1 I tensor, the identity matrix of this dimension. And the other SU2 is the same sort of structure, but the other way around. Now, it remains to verify that these two matrices commute with each other. these two sets of matrices commute with each other. And this is true because of these ones which are here, in a sense, and the way the tensor product works. So the point is that if I take this matrix, and multiply it by this matrix, now for the I can be different to the J, this is equal to, from the rule that we saw before, di J1 times the identity, which is just doesn't do anything, tensor d J2 J. And that is equal to J1. Sorry, it's a bit laborious writing all this stuff. Oops. That's also equal to this matrix. Sorry. Typo here. The multiplication of these two matrices, which is just the other, which is just the multiplication in reverse order. So these matrices commute with each other. So therefore, we now have a representation of the algebra SU2 plus the algebra SU2, which gives us representations of both SO4 and the Lorentz group by exponentiation. Okay, I'm going to stop there, but I can take some questions if you have them.
Yeah, Professor, so the conclusion is that the D tensor identity is a representation of the Ni, right?
Sorry, Johan, ask again.
So the conclusion is that the DJ1 tensor product identity is a representation of the Ni.
Yeah. Yeah.
Okay, and likewise for Ni tilde.
Yeah. That's
okay.
what I meant by this. See, when I wrote out the thing at the beginning, the point is that you've got two SU2s. And so I'm just taking a representation of the first SU2, and then I'm tensoring it with a representation of the second SU2. So you see the first guy depends only on theta plus, and the second guy depends only on theta minus.
Mm.
And so that's then when you follow the steps and you get the generators you keep track of the theta plus and theta minus, then you've got, you conclude, yeah, exactly what you were saying.
Okay.
Because we're taking the tensor product, they commute with each other and they have the same dimensions. Next
Professor.
time we'll, yeah.
Which is the difference here when you take the direct sum and the direct product?
What do you mean by direct sum? This?
Yeah.
No, this is just the notation which means that the two algebras commute with each other.
Okay.
Whereas, so that's just as abstract algebras, they commute with each other. The tensor product is only when you're dealing with concrete, matrices, representations, and vectors. So we don't take, and for matrices, the only notion of sum is actual normal addition of matrices. Did that answer your question?
Yes.
So we'll, this is probably a little bit fast at the end, so we will next time review this and start looking at some examples. Because I'll just finish with one, actually I'll write one final statement. Because all of the irreducible representations of SU2 are given by the spin given by the dj I matrices. The representations we have constructed give all of the finite dimensional representations of the two algebras and groups of interest. Does anyone else have any questions? All right, so tomorrow is the problem solving question session with Ida. I might pop in to see how it's going. And then we'll come back to this topic on Thursday. All right, so see you all.
Goodbye.
Bye,
Thank
Professor.
you.
Thank you.
Thank you.
Bye, sir.